New pictures captured by the James Webb Space Telescope have staggered specialists. Rather than merely extending our perspective on the universe, these photographs revealed an unsettling reality. Our perpetual perception is insufficient to make sense of the universe's early stages. The theory of the Big Bang appears to be reaching its limits, prompting us to consider new hypotheses about the origins of the cosmos. The question arises: how was the universe formed? And why does this new data challenge even the most experienced specialists to unravel the mysteries of the Big Bang? What if we re-examine the possibility that the Big Bang itself defies conventional thinking? The Big Bang was not an explosion in pre-existing space. Perhaps it was space itself that began around 13.8 billion years ago, alongside matter and time. A quirk in physics and cosmology describes singularities, points where gravity is so intense that the curvature of spacetime becomes infinite. Billions of years after the universe's beginning, we observe that our vast cosmic home is part of a grand, ongoing cycle. For specialists, this represents a fundamental aspect of the universe's existence. It is clearly an endless evolution. However, it is crucial to understand that the universe is not expanding into pre-existing space. Rather, space itself is continually stretching in size. According to current theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was when the first luminous celestial objects merged to form mature systems. However, how quickly these colossal systems formed remains a puzzling mystery. A wealth of data emerged from the first images captured by the James Webb Space Telescope in July 2022. Specialists revealed that the telescope had identified extraordinary galactic systems, some of which already existed around 300 million years after the universe's birth. Unlike the massive, permanent structures that formed much later, these early galaxies were significantly smaller and less massive. This aligns with a scientific model accepted by specialists. The density of matter in the early universe was simply not sufficient to create galaxies the size of those observed today. What began as the identification of 6 glowing red-shifted spots from the James Webb Space Telescope ended up triggering one of the most significant cosmic mysteries in recent years. Although these newly discovered galaxies are similar in age to more recently recorded ones, they are nearly as vast as our own Milky Way. This has created a fascinating enigma. After analyzing a series of images captured by the near-infrared camera, specialists identified the aforementioned light sources. Using redshift, they confirmed that the light from these objects took over a billion years to reach Earth. Thus, these structures existed around 570 million years after the Big Bang. By examining the characteristics of these systems, researchers concluded that the Webb telescope had captured 6 early galaxies. Incredibly, these galaxies were so massive that they challenged conventional theories in cosmology. Instead of finding the expected smaller galaxies, structures nearly as wide as the Milky Way were identified, despite forming early in the universe's history. If this finding is confirmed, it suggests that much more matter existed in the early universe than previously assumed, posing a significant challenge to existing cosmological theories. If even one of these enormous systems is genuine, it would upend prior assumptions. To account for this phenomenon, the density of matter in the early universe would need to be several times greater than previously predicted. Another, equally strange explanation depends on how these grandiose systems formed, something still completely unknown to us. These discoveries and the debates surrounding the Big Bang have led some researchers to diverge from this hypothesis. Various astrophysicists with alternative perspectives feel their views are not adequately represented in scientific journals. Those who express doubts about existing theories are often labeled as irrational. However, even advocates of the Big Bang theory continue to grapple with questions that lack convincing answers. These questions include fundamental issues like: why and how, 13.8 billion years ago, did something arise from nothing? Could something truly come from nothing, or was there a triggering event? Or was it all a coincidence? Steven Weinberg pointed out that the concept of time as we understand it began only with the Big Bang. Thus, this event could not have been triggered by something external to it. A similarly perplexing question relates to the uniformity of radiation and density throughout the universe. Regardless of the direction or distance we observe on a larger scale, we find similar densities and distributions of galaxies, nebulae and radiation everywhere. Standard models explain this anomaly through the theory of inflation. However, some researchers take this idea further, proposing a theory of eternal inflation. According to this concept, inflation has only stopped in specific regions, like bubbles, and continues endlessly elsewhere. This suggests that multiple universes could be forming in these bubbles, each with its own unique physical laws. In this model, a key question arises. What if our universe does not represent the entire picture? More intriguingly, what if another universe existed before ours? In this scenario, the Big Bang would be part of a larger cycle. According to this view, our universe is part of a greater multiverse. Within this framework, the possibility of an eternal cycle of decay and renewal of universes is advanced. However, this is not the only perspective presented in the field of cosmology. In 1955, for example, an article in NASA Spacetimes argued that there may never have been a Big Bang, suggesting instead that the universe has existed for an infinite amount of time. In this view, the expansion of the universe would be non-existent, and the observed arrangement of matter could give the illusion of constant evolution. Additionally, another fascinating hypothesis emerges from the field of quantum mechanics, physical science and string hypothesis. A few examinations have recommended that our universe and everything in it could essentially be a flat, three-dimensional image projected onto a surface. Subsequently, there is a possible thought that our reality is the consequence of a more elevated level simulation. While this may seem like the plot of an eccentric sci-fi film, it could potentially be connected to the Kardashev scale, which measures the degree of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully harnessing the energy of an entire universe, it might have created an astonishing simulation. Understanding this concept is a genuinely tangled matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited discussions about the true nature of our world, challenging established theories and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the core of this inquiry lies the hypothesis of how things came to be, a foundation of modern cosmology. According to this hypothesis, around 13.8 billion years ago, the universe emerged from an extremely dense and hot state, rapidly expanding and resulting in spacetime and matter as we understand it today. This extraordinary event was not merely an explosion within pre-existing space but may have marked the actual beginning of space itself. The concept of a singularity, where gravitational forces are so intense that spacetime becomes infinite, supports our understanding of this early stage of the universe. However, the discovery of early systems by the James Webb Telescope challenges assumptions about how quickly structures formed in the universe's infancy. These systems, detected within a few hundred million years of the Big Bang, appear phenomenally developed and massive, defying assumptions based on current cosmological models. One of the significant questions raised by these discoveries is the nature of inflation. As proposed by the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand rapidly and uniformly. This rapid expansion explains the consistency of the cosmic microwave background radiation observed across the universe today. However, the new findings suggest complexities in the early evolution of the universe that may require adjustments to inflationary models. The formation of galaxies like those observed by the Webb telescope forces cosmologists to reconsider the conditions and processes governing the universe's early development. These massive systems, both colossal in size and mass, suggest a matter density that exceeds previous estimates. The mystery deepens as scientists consider how such enormous structures could have formed and evolved in such a relatively short cosmic timeframe. Furthermore, the discovery of these early systems raises intriguing questions about the nature of dark matter and dark energy, two elusive components that constitute the majority of the universe's mass and energy. While dark matter is understood to provide the gravitational foundation for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is merely one among many in a vast multiverse, each with its distinct physical laws and constants. These ideas, emerging from developments in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One concept gaining traction is that of eternal inflation, wherein universes continuously emerge from a larger, expanding space. This theory implies that our universe may be just one bubble among countless others, each with its unique properties. The challenge lies in finding observational evidence to support such speculative ideas, as they push the boundaries of empirical verification. Another provocative hypothesis is that our universe exists within a simulated reality, much like a computer-generated game. This idea draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable accuracy. If true, our perception of reality as a singular physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. Moreover, advancements in observational cosmology continue to uncover the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with its unprecedented sensitivity and resolution, promise to unveil even more hidden secrets of the cosmos. Future observations may shed light on the earliest moments of the universe, providing insights into its ultimate fate and the fundamental laws governing its evolution. Beyond observational cosmology, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three major forces, strong nuclear force, electromagnetism, and weak nuclear force, remains a central goal of theoretical physics. Concepts like quantum gravity and string theory offer potential frameworks for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Time, as a linear progression from past to future, is challenged by quantum theories suggesting that time may be nonlinear or even illusory at a fundamental level. Understanding the nature of time within the context of cosmological models could reshape our view of the universe's origins and evolution. Furthermore, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope study of exoplanet atmospheres, might provide evidence of biosignatures indicative of life beyond Earth. Despite these scientific endeavors, cultural and philosophical reflections on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration provoke thought and discussion across disciplines. As we stand on the cusp of a new era in astronomy and cosmology, driven by technological advances and theoretical breakthroughs, we are reminded of the vast interconnectedness of everything, from the smallest subatomic particles to the immense cosmic structures spanning billions of light-years. The universe reveals its secrets to those willing to explore. Ultimately, the study of the universe and the origins of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe, raising new questions about creation, evolution, and the future. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic evolution, we move closer to a deeper understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a grand journey to decipher the cosmos, a quest that promises to reshape our understanding of existence itself. Whether exploring the depths of black holes, grappling with the motions of distant galaxies, or examining the nature of reality, each discovery brings us closer to unraveling the intricate tapestry of the universe. As we venture further into space, driven by curiosity and a desire to comprehend the universe's vastness and complexity, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment captures the essence of scientific inquiry, an unending journey of discovery, wonder, and illumination that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the cosmos and ourselves. Thus, the exploration of the universe is not merely a scientific endeavor but a profound human quest for knowledge and meaning, an odyssey that transcends the boundaries of space and time, inviting us to reflect on our position in the grand tapestry of existence.